Swayam Prabha. Digital India. Educated India.
Dear participants, as in the last week also we have discussed bioprinting of different tissues and organs. Like we have till now we have discussed bioprinting of vasculature and then bioprinting of cornea. So this week also we'll discuss bioprinting of several other tissues. So one such tissue is the heart. So here we'll discuss how we can print like different heart structures like a myocardial patch or maybe the whole heart model. How can we develop different types of heart structures with bioprinting? Before that, let us discuss why why bioprinting of heart or heart-like structure is important. What is the need for this thing, and what are the different strategies? Right. So first thing is, let us understand what is the need here. If you see there is a rise in heart related diseases like heart failure or maybe heart attack due to or by myocardial infarction, right? What? And also there are several other end stage diseases, right? And there a large number of populations, especially in India, they suffer from this kind of heart diseases, like where suppose there's a heart attack where a particular patch of heart muscle is not working anymore. So then we need to generate a cardiac patch to support that particular area to regenerate and to again come back to functional state where then the whole heart can function in a better way. So there is a tremendous need of development of a cardiac patch or even the whole heart by by printing. So if you see the heart, then it is composed of fully differentiated cells, like there are cardiomyocytes, then other types of cells, and they are mainly organized to constitute the various anatomical elements of that heart tissue. And there are different hierarchy, different level of the tissue is present at different scales, like there are some microstructure is important, and also somewhere the macrostructure of the tissue is very important. And heart, another important thing is the heart is a highly mechanically active tissue because it need to pump the blood to the whole body. So the heart muscle, that's why typically heart muscle, they are thick muscular tissue. Because of this they have to pump that kind of that ability should be there. But the most important thing to understand here is that the cardiovascular tissue, they exhibit very limited ability to self-renew after injury. So if there is any kind of injury, any kind of defect or disease arises in the heart tissue due to some disease or maybe injury, that is the in case of adult population, that is very difficult to regenerate, right? So some interventions is required from outside, like say that's why extensive intervention may be required at the later stage of the heart cardiovascular diseases where the heart does not self renew or heal by itself. So we need to intervene, we need to provide certain some we need to develop a strategy to provide certain supportive structures, probably a bioprinted heart muscle or a patch to support that kind of that injured tissue. And if you see over the years, people have been using different strategies like mechanical valves have been used to replace the heart valves or diseased or damaged heart valve, so that the heart valve, the main function of the heart valve is the to prevent the blood flowing in the opposite direction, right? And when it opens, then the blood can flow through that one. So it basically it controls the blood flow through this thing. So by doing closing and opening of that valve. So valve is a tissue that is also mechanically, it is highly, the mechanical requirement is very high here, because the tissue is continuously, it is yeah, is getting like is under agitation, and it is getting either constrict, means it contracts and relax. So because of that, it probably the valves get closed and opened, right? Either it can be tricuspid or bicuspid. In both cases, the cusps that closes and opens. Because of that thing, the blood, it can maintain the blood. It can control the blood flow. Whenever it is closed, the blood flow is stopped, and then when it is open, the blood flow starts. So the heart valve is a highly tissue where this in certain cases there can be damage to the tissue. So that time we need to replace the heart valve, and mechanical heart valves are mostly used because of their, because they have done a great job over several decades. They have been used, but their limited efficacy in pediatric patients. But if you think about the pediatric patients, for children, where, because the children, when the children is growing, their heart size also grows, but this mechanical device, they cannot grow with the patient. So that time there is a challenge, there can be a mismatch, and there can be loosening of the heart valve from the tissue, and then that cause a huge challenge for the pediatric patient. So we need to come up with some strategy where we can, this valves, if the valves can be replaced, suppose with bioprinted heart valve, that would be wonderful. And if you see in there are many patients who are waiting for transplants, like heart transplant, because there's some damage or disease to the heart. That's why the heart transplant is required for some patients. And but if you see there is a huge waiting time for that to get a transplant, because of there's a limited amount of supply and the demand is huge. But those patients are mostly, they are on ventricular assist device, when that device actually helps them to pump the blood to the circulate the blood to the other organ. Another thing, there is another development, that total artificial heart has also been there, and it is also proven successful, and it can be used to replace the actual original heart, so that it takes care of the blood circulation inside the body to the body. But there, where these are very expensive, and it is not affordable by many people, so that affordable is the concern for that kind of total artificial heart. So the goal of this tissue engineering or bioprinting is to replace the native heart tissue with a functional heart developed by this bioprinting process. So functional replacement with transplantation, that is the final goal of all these things. And in this lecture, in this course, we'll discuss some of the strategies and some of the attempts, but there are many more studies. Please go through the literature. I have selected a few study to discuss in this course about the thing, like, so there are various other studies and various strategies exist. So in the first one I have selected, that is how to print a bioprinting of a cardiovascular network, strategies for bioprinting cardiovascular network. If you see the vascular, we have already discussed about the vascular tissue printing, where we have discussed various strategies. But if you see in the cardiac muscle, the blood vessel network, the vascular network is highly complex, and they are supplying blood, they are supplying nutrients, oxygen to the cardiac muscle, because the cardiac muscle, they are highly active, they are metabolically active, they need a lot of oxygen, because they are all the time, they have been under their contraction and relaxation that is going on. So that blood vascular, so this is a very complex vascular network, and for to bioprint that, this is really challenging. Other thing is, when we start to use bioprinting for replicating or fabricating any part of the heart, any type anatomical structure, or any particular structure, or when we try to print that but with the blood vessels, vascularized muscle, suppose the vascular heart muscle, then replication of that particular anatomical structure and physical characteristics of the blood vessels are very important, so that we can generate that a artificial heart, or a part of that heart, and that should have the function that is required, right? So when we print a blood vessels, as I have discussed in our earlier lecture also, then we use actually different strategies to generate a blood vessel. Either it can be, if you suppose if it is a bigger blood vessels or smaller blood vessels, we use different kind of strategies. So these are for these following are the methods by which a vascularized tissue, especially for heart, vascular cardiac tissue, or can be printed or have been tried, right? And we have also seen indirect bioprinting. We have already discussed in our earlier lectures, where use of a sacrificial material is very important, and the sacrificial template is basically used and to form the open channels in the solid construct. Suppose we print within a hydrogel. In the hydrogel, we print the sacrificial template first, then we print the hydrogel, or we can put the hydrogel in that, and later on that template sacrificial material can be taken away, but it will leave a vascular network structure or a channel structure. So that channel can be further used to supply to perfuse to this thing blood, to perfuse media or other things, so that the tissue can survive and survive. But when it will be actually implanted, that channel can work as channel can connect to the pre-existing blood vessels, and then the blood can supply within this in the tissue. The other strategy we have discussed earlier, that printing the channels can be directly printed into the construct. Like suppose when I print the construct, in that printed construct, we can print the channels in the particular the network, vascular network we can create there with suppose with the required cells and bioink. That can be another strategy by which a interconnected network can be directly printed in the construct itself. The other thing is direct printing of tubular blood vessels in a vascular network. That is also another strategy, where suppose a coaxial bioprinting method can be used, where we have seen this earlier also, we have discussed this, that in the coaxial, suppose there are two concentric nozzles. So where the inner core, there is a core nozzle and the surrounding nozzle. Through the core nozzle, suppose if we send a cross-linking material, and through the surrounding channels, if we print the bioink, that is our that blood vessels ink or bioink, that if we extrude them, then what will happen, the through the luminal area or the core channel, if we send the cross-linker, that cross-linker will cross-link that, because here the bioink, that will, when it will extrude, it will come as a tubule, the tubule format, tube format. So that tubular structure can be cross-linked from the inner by using the cross-linker from the inside out, right? So we have discussed this also. So these are the main three strategies by which vascular tissue can be printed. First thing is by printing a sacrificial template and then putting the gel on top of on that, then take out the sacrificial template, and then we can get a vascular network. The next thing is the channels can be directly printed with the, here also the sacrificial material or a vascular tissue bioink can be used to print the channels within the construct. Other thing is the direct printing of tubular blood vessels in the vascular network. So where it may be a coaxial bioprinting can be used, or different other techniques can be used to come up with the blood vessels. But there is till now whatever the studies are done, those studies are mostly very early, and these are mostly preliminary methods, but they are not sufficient to generate a clinically relevant heart tissue. With this method, we can generate suppose a patch or a part of the structure, suppose the heart valve or cardiac patch or some other structure can be printed, can be biofabricated, but to print a full heart cannot be printed with this kind of support structure. And the other thing is the strategies for bioprinting of cardiac patches. So where there are several studies where researchers have tried to replicate the anatomical structure of the muscle with, suppose, with embedding vasculature or without the vasculature also. So that can be used as a cardiac patch, and that can be used for people with myocardial infarction. Suppose in case of myocardial infarction, when suppose a part of the muscle is injured, a part of the muscle is dead, so that can be replaced with, for myocardial infarction, that can be replaced with the bioprinted cardiac patch. And if you see in literature, both the processes, laser induced forward transfer that we have discussed earlier, and extrusion bioprinting, we have discussed these two methods earlier. So they work on different principles. Extrusion, where we extrude the material in the form of filament, then we print a structure. In a laser induced forward transfer, with the help of laser, we actually forward transfer the material from the ribbon to the stage. So these two methods have been well used for generating cardiac patches with angiogenesis and at the age of the myocardial infarction, and that can be put in the at the myocardial infarction site, and but that has shown huge promise to preserve the cardiac function. Suppose in case after acute MI, when a bioprinted patch was developed and that has been put into that area, then implanted in that particular area, this defect area, then it actually helps in regeneration of that cardiac patch, cardiac muscle. But again, the most important thing, the cardiac function can again be fully re-established. So these are very powerful technique by which cardiac patches can be used. And there are reports where they have used desolarized heart ECM bioing to print that patches. Why desolarized heart tissue bioing? Because if you see the tissue can be divided into two components, at least acellular and cellular component. The cellular component, where suppose all the cells are present, and those cells are there are different types of heart cells suppose is present. The other thing is the acellular part, where the most of the matrix components are and proteins and other things, those are mostly present, and then they can actually uh, they can help, because they can provide a natural microenvironment to the tissue, and so that the cells, where if we put the cells in that area, then that they can actually help to grow the cells, to induce their growth. Certain cases, if we use stem cells, then this digitalized tissue specific bioing can also induce, or can also induce differentiation of the stem cells towards this particular tissue lineage. So digitalized tissue specific bioink is very widely used for different applications, and these are very much useful. So the major advantage of using uh, tissue specific bioink, like in this case, suppose the heart tissue bioink, is like they provide a suitable biochemical and biophysical microenvironment for cell differentiation. So where suppose in this particular work they have used a cardiac progenitor cells and stem cells, and then those things actually they have put into or they have loaded encapsulated into the ECM derived bioink. Because this ECM derived bioink, they provide a natural microenvironment, a natural mimicking or biomimicking microenvironment. So the stem cells can differentiate towards these cardiac parasites, because this DCM bioink, they also have some growth factor, resident growth factors, bioactive factors that induce differentiation of these cells. Another important thing is, when they implanted this cardiac patch generated by this extrusion based bioprinting with the digitalized tissue specific bioink, it shows that the cardiac patch demonstrated enhanced cardiac function with minimal infarct complications and promote robust vascularization within the engineered tissue matrix. So this cardiac patch actually it helps in to gain that tissue. It heals the tissue first. That the MI infected. Suppose the MI infected dead tissue, so it helps to regenerate that area and also re-establish the cardiac function. And there are many limited infarct complications, and also robust vascularization, so the tissue will survives because of this robust vascularization. If the vascularization can be there within the tissue, within the bioprinted tissue, after suppose of course after implantation, it helps in uh, growth of that particular tissue, and also the tissue regeneration, tissue remodeling of that particular tissue will be excellent. So I have mostly discussed from these two literature. Please go through this literature for further details about their work. These two are very important work for to generate the generated myocardial cardiac patches for myocardial infarction. Now I'm going to discuss another important work where it is published by Noor et al. In Advanced Science Journal, where they have actually shown a schematic of generating personalized cardiac patch with a biomimetic approach, like with by it's a personalized, so it can be from the patient, it can be from the patient. And omentum tissue, omentum is present in the in our peritoneal cavity, where the in the peritoneal cavity there are other organs. So it is this is the lining of that organ. So this omentum is a highly vascularized fat tissue. So they extracted this, suppose the omentum tissue can be extracted from the patient, and then because this tissue as a cell, this tissue is composed of both cellular and cellular component. So the cells can be separated from this tissue, and also the material can be separated, or the ECM, extracellular matrix, can be combined. Suppose the cells are isolated first, and then the matrix, the remaining matrix, can be also developed into a hydrogel. Now this process, this tissularized tissue, so first the tissue is, the cells are separated, then it is the tissularized tissue, and that tissularized tissue, because this momentum tissue is also composed of all the different material like collagen, gags, and other things. So this thing, again there's a process, suppose a process is a typical protocol is there, where this this tissue is again solubilized into a hydrogel by using that, by dissolving that tissue in a acidic solution with the help of pepsin or some other enzyme, and then it can be a hydrogel can be developed. But the important thing here, because this tissue is composed of mostly it is collagen and some other material, so the collagen can again, after if we dissolve the collagen, that there be that the collagen can go into the solution. But again, if we optimize the pH, so the tissue again, the pH, if suppose for solubilization, a lower pH is required, but again the pH is again can be brought back to physiological pH. That time the tissue can be, the hydrogel can become. And if we incubate that at 37 degrees centigrade, then the collagen self assembly will start. And because of this thing, this hydrogel is a thermos responsive hydrogel. But because, and another thing, it is because it is taken from the same patient, so it's a personalized thermos responsive hydrogel. And then that personalized thermos hydrogel can be used to develop the bioink, where from the same tissue, as I said, from the same tissue the cells can be isolated. So in this case, suppose the cells, resident cells from their cell can be isolated, then they can be reprogrammed to become a stem cells, like induced pluripotent stem cells can be generated from these cells, because here the mostly fat cells and other cells are present. From there that can be generated, a that can be reprogrammed to first induced pluripotent stem cells, and from there again it can be differentiated towards the primary cells like cardiomyocytes and endothelial cells. Cardiomyocytes will for the, suppose for the patch, and endothelial cells for the blood vessels. So these two things, again these two things are can be incorporated within this personal hydrogen. Then we can have a bioink formulation. So one bioink can be for the cardiac tissue specific, like that is the other we can contain cardiomyocytes. So it can be the matrix mate for the printing the whole structure, and then the endothelial cells, when it is implanted incorporated within the bioink, it can be used for the blood vessels. So these two things are there. Then they have used a dual extrusion bioprinting methods to print that structure. Like suppose the blood vessels can be printed like this, and then the with the cardiomyocytes bioink, that can be used for printing the structure. So then that can be used for either to make a cardiac patch with vascularized embedded vasculature, and also it can be used for a heart-like structure, right? And then after maturation, that can be implanted to that particular diseased, that disease or disease, that suppose it's, if there is a MI, so that MI infracted, sorry, myocardial infracted area, where that the patch can be implanted, and it can help in the regeneration of that particular patch. So this is the schematic to generate how to for generation of a personalized thick cardiac patches personalized thick and vascularized cardiac patches using patient's own tissue using 3D bioprinting approach. Now, for generation of these blood vessels within the tissue, what they have used, they have actually used a CT image of that patient's heart. So the patient's heart, suppose the patient undergoes CT scanning, and by this way we can get the slices of that images, like the patient's images of this particular tissue. From there, actually, we can extract the left ventricle coronary arteries. So we can extract the coronary arteries. This, how does this is, suppose this is from this part, this coronary arteries, these are extracted, and these are again modeled to these are modeled to understand this thing. But when they model and then they do some simulation study to understand how the oxygen concentration will be there in, supposing this is a patch where this kind of vascular tree is designed based upon from the CT data. Now you can clearly see here from this way, and here it is. This is the scale tells you the oxygen molar concentration here in the tissue. So you see that the cells present near to that coronary artery, there the oxygen concentration is high or good, but in the other area concentration is very low because the oxygen cannot diffuse to the large area within the construct. So a further optimization is required to generate the blood vessels, the vascular tree. So again they have come up, suppose this is again they have come up with a replanning of this vascular tree. In this case, if you see, most of the part of the tissue they are getting good amount of oxygen, so the tissue cell survivability will be good in this case. So this is how from the CT data you can extract, basically you can extract a particular tissue structure that is based on your interest, and then you can remodel that, model that in a particular structure, and also you can use that for generation of that vascular tree, and you can work on that thing to generate the whole tissue construct, so that you can replan that to have a better vascular tree, so that the whole patch can be very well vascularized. Then they have used the same vascular concept to fabricate a cardiac tissue patches, where this is the strategy where they have used a uh, two bioink that's mostly used, where they have these cardiomyocytes, and for the tissue that bioink is used, where the cardiomyocytes are there, and in the sacrificial layer method where endothelial cells can be also be there, and then they can print a vascular tree. Here actually this they have used, we have earlier discussed this concept that a sacrificial network can be used for to generate the vascular tissue construct. So they have used the same concept here with the endothelial cells. A sacrificial vascular network can be printed, and then this the other tissue, the tissue with the bioink with cardiomyocytes, that is printed on here. By this way they have generated, then the sacrificial material is taken out and endothelial cells are put in the that vascular network, and then you can get a vascular channel. Here A tells you the 3D model of the cardiac patch, B tells you the side view of that printing concept, and distinct cellular bioinks. Two different bioinks are used, and a printed vascular cardiac patch is can see here, where the vascular channels can be clearly seen. Those are the mostly the secretion where the material is taken out. Then you can clearly see this thing. The cell viability is very good after printing. So this in this case the printing process that doesn't induce any cell toxicity, and a bioprinted vessel can be clearly visible here, continuously layered with endothelial cells. Because the green color is because of the GFPs, and the endothelial cells can be clearly seen. They have fully populate the vascular channel from the luminal side, and you can see clearly blood vessels here. And then here the cross section of the this is the thing, the printed iPSC's derived cardiac patch, where the blood vessels can be clearly seen. The CD31, the expressing blood vessels can be clearly seen here. And cross section of the single lumen. If you get further uh, magnify it in, and then if you see the under the cross section, you can clearly see the endothelial cell they covered the line of that channel luminal surface, and the other cells are clearly visible. here the fibroblasts, they are expressing the RFP. There is a red color thing dot dye. So that is the here the other cells, fibrous cells are clearly visible. The surrounding area, endothelial cells, there is that cells typically consider the lumen. Then they have done further characterization, further study where a cross section of that wall is clearly visible. Where the see, if you see again further cross section of the on the wall of that luminal wall of the blood vessels, the GFP endothelial cells, they are expressing GFPs, and the fibroblasts they are expressing RFP red. Those things are clearly visible. Again, in the eye, you can clearly see the channel dimensions here, right? The calcium imaging with printed vascular pad. The separate region of interest are represented in different colors. Here, the calcium image with calcium imaging also we can clearly that suppose the different parts of this thing, the parts of this of the patch where they do the calcium imaging, then calcium from the calcium imaging also you can clearly see that you can quantify the calcium activity within the cardiac patch. So quantification of calcium transient across the lumen of the vascular cardiac patch, like here across the lumen of the thing, how they quantified the calcium transients on the across the lumen, and then they have transplanted that thing, that cardiac patch, in the again in the omentum, in the rat omentum, in between the layers of the rat omentum, where they have implanted this. Here the red the white dotted line that demark that the bioprinted cardiac patch where it is implanted in this thing. Then sarcomeric actinin, is the very important for cardiac tissue, and it is by red color thing you can clearly see the this thing within that tissue, that is the cells or the patch that they are expressing this sarcomeric actinin, and blue the nucleus is stained by the blue. This the structure, the cardiac tissue specific structure is highly can be visible here by the printed structure. They have also implemented another strategy for uh, personal hydrogen supporting bath. By this supporting bath concept, we have seen 3D printing in support bath. We have discussed earlier in our earlier classes where here what they have done, they have printed that sacrificial material and the blood vessels material both in the support medium. And this, as this material is as the thermoresponsive hydrogel, so they have printed at very low temperature where the support bath, and they have increased the temperature of the support bath to 37 degrees centigrade, where the material get cross linked, and also the support bath material can also be removed by removing by the, because at the 37 degrees centigrade they lose their structure, and it becomes a fluidic structure, fluid like material, and that can be taken out, and you can get your printed structures, right? So here with that desolarized tissue, desolarized tissue hydrogel, they have printed. You see here, lattice structure is printed here. Multi-layer viscous lattice structure is printed here within the support bath material. And then when they remove the support bath material, before after that, the structure this look like similar to this. And in no hair, the viability is maintained, and you can see in culture, printing and extraction, after all the steps, viability is maintained, and there is no significant difference between the cell viability during culture and during printing, and after printing and after extraction. They have also shown that you say here this is the configured structure of the two-layer printed structure of that with their desolarized tissue bio, and then also shown that a complex, highly accurate, high resolution thick structure can also be printed with the personalized hydrogel, like from the G and H. These two are two different structures printed with the same hydrogel that they have developed, and that can be, but and then that can be. So this the important thing is this hydrogel can be very well used for printing different types of complex structures within the hydrogel. So that is the possibility with this hydrogel. There are several other studies where either people have tried to bioprint a cardiac patch with cardiac tissue specific ink, by developing cardiac tissue specific bio-ink, and also using different types of materials. Please go through the literature. There are several studies on this. Now let us understand what are the challenges of doing heart bioprinting. Suppose if you want to print a whole heart, then you can understand the requirement of the cells. Billions of cells are required to print a large tissue. The first thing is how to get that amount of cells from a tissue. Suppose we can collect a small biopsy or some tissue from the patient, but we cannot isolate billions of cells from a small patch of tissue, but we cells. So again, we need to expand that cells, and but we need to take care of during expansion. They do not lose their phenotype and genotype, so that the cardiac tissue specific the properties should be maintained. Other thing is also other source. Maybe we can isolate stem cells from that patient, and then we can program them to or differentiate them toward cardiac specific cardiac lineages. Or other thing is also maybe we can collect as the earlier work they have discussed, that we can collect the tissue, we can collect the cells, collect the tissue. So like some omentum tissue. Omentum tissue is mostly can be safely harvested from a patient, and then we can isolate cells from that. Like suppose stem cells, we can isolate either stem cells, or we can also isolate primary cells, and then we can de-differentiate or reprogram them into induced pluripotent stem cells, and then further we can also differentiate them into cardiac tissue specific thing. So there, so so the strategy for generating that many cells, that is challenging, and that has to be tackled. Other thing is we can also need to scale up the manufacturing process to generate this kind of cardiac patches, by which we can suppose we can generate a large piece of tissue, multiple tissues constructs also we can generate. So the manufacturing challenge, yeah, this is manufacturing challenge, how to scale up that whole process so that we can come up with a tissue. Other thing is the standardized regulatory process is very much important for translation to the clinic. So these are regulatory challenges where we need to so they specific standards are required to be developed, by which we can actually assess the bioprinted tissue for their safety and efficacy, and by which so that then that can be used for this thing. Also, the addressing the biomechanical requirement and longevity of the tissue engineered organ, that is another important thing for bioprinting. By which we can actually, if we need to understand the biomechanical requirement, and if we can address that, and if also the bioprinted organ, they can be cultured for longer duration. So the longevity of that bioengineered organ is two very important points for culture for heart tissue bioprinting. So these are the few examples I have uh, given. I have selected for this particular lecture for heart tissue bioprinting, but there are many more studies. I encourage you to study. I encourage you to go through the more literatures for bioprinting. You will understand much better. Thank you very much for attending this lecture.